In today's lecture, we will be discussing about the stability considerations and methods to encounter the problems that occur during the formulation of emulsions. Dispersed systems are the formulations which are biphasic. In these formulations, one phase is dispersed as dispersed phase in the other phase known as dispersed medium. These systems have two phases, hence they are known as biphasic. One phase is considered as internal phase, the other phase is considered as external phase. Internal phase is also known as dispersed phase. External phase is also known as dispersed medium. These dispersed systems are majorly classified as suspensions and emulsions. In today's lecture, we'll be dealing with the stability considerations in the manufacture of emulsions. In this lecture, we'll be discussing about the methods to assess the stability of emulsion, and if the given formulation or if the resultant emulsion is unstable, how can we overcome this instability problem? How can we improve the stability of an emulsion? Now, let us consider the stability parameters in an emulsion. An emulsion is said to be a stable one if internal phase is uniformly dispersed in an external phase, if the dispersed phase is uniformly distributed in the dispersed medium. All the globules present in the emulsion should not fuse with each other, should not coalesce with each other. All the globules are to be uniformly distributed as separate entities. They should not be fused together. If all the globules fuse together or coalesce with each other, this leads to phase separation. Now, let's consider this instability in detail. Now, majorly the instability problem in the pharmaceutical emulsion is categorized into 4 different categories. The first one is flocculation. Flocculation and creaming goes hand in hand. Flocculation, the name itself indicates grouping of all the globules together to form a larger globule. In case all the globules come together and form a larger globule, it leads to the separation of the oily phase and the aqueous phase, which results in instability. And if in case the oily phase and aqueous phase, if the density differences between these two phases is much larger, it results in the upward creaming or downward creaming, which indicates separation of 2 different phases. Now, if in case flocculation is left as such, if that is not encountered, all the globules will fuse together to form a larger globule, and this causes a separation of oily phase away from the aqueous phase, thus resulting in the separation of two different phases. The second one, coalescence and breaking. Now, if the flocculation is left unattended, now if we being a pharmacist, if we are not able to encounter this flocculation problem, now this results in the complete separation of phases. Coalescence is a phenomena of the fusion of all the globules to form a larger globule, and then a complete separation of two different phases occur that results in breaking of an emulsion. It is an irreversible phenomena. Breaking of an emulsion is an irreversible phenomena in which complete separation of the oily phase and the aqueous phase is seen. And the other unstable consideration include physical and chemical changes. This physical and chemical changes, the name itself indicates that there will be some changes that occur in the formulation of an emulsion. It could be because of the wrong choice of emulsifying agents, or in addition of emulsifying agents in wrong proportions, and even the nature of the emulsifying agent plays a major role in the deterioration of an emulsion. Let's see all these factors in detail. The next one is phase inversion. Phase inversion is a phenomena where the inversion of different phases, like inversion of the aqueous phase and the oily phase present in an emulsion, occurs. The name itself indicates the internal phase, the supposed to be internal phase becomes the external phase, and the external phase tends to be the internal phase. And this happens when a proper proportion of internal phase and external phase is not maintained. Now, these are the stability parameters that are to be considered, that are to be kept in mind while preparing an emulsion. Now, this physical instability of emulsion is explained by this figure. Now, these are the physical instability problems that we see during emulsion formulation. The first one is the coalescence, where the smaller globule will come together to fuse with each other to form a larger globule. A smaller one will come together to form a larger globule. Now, if this is left unattended, all the smaller globules, they will tend to come together. They'll form a group of smaller globules. Now, if these group of smaller globules, they stay there for longer time, it leads to the fusion of the smaller globules into a larger one, like this. Now, if these globules, they increase in their size, the increased globules come together and fuse with each other. Thus, all the oil particles or the oil globules get separated from the aqueous phase. So there is a separation of the oil and the water layer. Now, there is another instability consideration that is to be taken into account is creaming. Creaming is the phenomenon where the migration of the oily phase and the aqueous phase is seen. If the density differences between the oil particle and the water particle, or the oil globule and the water particle is more, then there will be migration of the oily phase and the water phase. If oil is much less denser than water, all the oil globules will tend to float and they form as a cream, as a layer. So if the one phase is much less denser, it tends to float and it tends to migrate onto the upper surface of the formulation. And that phenomena is known as upper creaming. And if one phase is much denser than the other phase, that phase will tend to form a sediment. This is known as downward creaming. In short, creaming is a phenomenon of separation or the migration of the phases depending upon their density differences. Now, breaking is a phenomenon where a complete separation of oily phase and the aqueous phase is seen. So this is irreversible. When once an emulsion is broken down, it cannot be reversed. So this is a complete and permanent unstable situation or the phenomena that is seen if proper emulsifying agent is not used, if proper concentration of emulsifying is not used, if proper combination of or the proper ratios of internal phase and external phase is not used. So these are the considerations that are to be taken into account in the preparation of emulsion. Now let's see how can we assess or measure the stability of an emulsion. Now we will be discussing about stability assessment of emulsions. Now, we being a pharmacist, it is really important to assess the stability. If the given emulsion is not stable, we need to know what are the various factors that can be altered to improve the stability of an emulsion. As the creaming of an emulsion plays a major role in deciding the stability, we need to know how faster our emulsion tends to cream, how faster our emulsion tends to sediment into two different layers. So in this assessment, it is really very important to take into consideration of globule size, number of globules present, and we need to determine size frequency of globules or particles. These are the three different important parameters that are to be considered when we are assessing for the stability of an emulsion. Now let's get into this topic. Emulsion has internal phase and external phase. Internal phase is distributed as globules in the external phase. Now, we being a pharmacist, we need to study the changes that occur in the size of the globules. We have seen in the flocculation and coalescence where the globules will tend to come closer and fuse to form a larger globule. If there is a change in the size of the globules, for example, in the beginning of the study, if the globule size is small, and during the study, if the globule size increases, it represents fusion of globules, which in turn reflects the ease and instability reaction that's happening in our emulsion. So we can decide the emulsion will it be stable enough within a given shelf life or not. Now for this, we will be considering a basic method known as microscopic method. Microscopic method, the name itself indicates, we'll be making use of microscope along with micrometer. Micrometer is a device which has two units, stage micrometer and eyepiece micrometer. Now this is a basic and simple laboratory procedure where we'll be measuring the globular size of in an emulsion. Now we will be setting up the microscope. Over the stage we'll be placing a stage micrometer. Stage micrometer is a slide having graduations. Eyepiece micrometer is eyepiece micrometer is a optic disc that is supposed to be placed in the eyepiece of an microscope. Now these two micrometers are graduated at the micron level. Now when we see through this eyepiece of the microscope, we'll be able to see graduations at the micronized size. Now when we place our sample onto the stage of the microscope, we'll be able to see the globule size, and at the same time we can measure the globule size in micron level by the help of the graduations that are already present over the micrometer. That is how we can easily measure the size of the globule. Now at the end of this experiment, we will be having a data of the size of the globule and the number of globules per square area considered. Now, this type of study is known as size distribution study. Size distribution study is to be carried out at different time intervals. After we measure the size of the globule, now let's see what are the steps how involved in this microscopic method. First, we'll be setting up the microscope with the stage micrometer and eyepiece micrometer. Then we'll be putting on the sample on our slide and place it over the stage of the microscope. Now observe the size of the globule. Now the first step would be note down the globule size. It will be in micron level. And next, note down the number of globules per square mm. And now note down the number of globules having specific globule size. This is really important. Why? Because it is from this data we'll be able to assess whether our emulsion is stable one or unstable one. Now, for example, consider a particle or globule is having 5 microns size. Now, count and sum up the number of particles that share the same size. So, number of particles having size 5 is equals to. So say for example, if the number of particles having size 5 microns are 9. So we need to make sure the number of particles having size 6 microns say. So if we are having number of particles having size 6 would be 10 say. So likewise, we will be having certain data having the number of particles having or sharing the same particle size or same globule size. Now we need to plot a graph by taking particle size on x-axis and particle number of particles or the size frequency distribution on the y-axis. Now let's see how can we plot this graph. Now in this we need to plot a graph by taking particle size on x-axis and frequency on y-axis. Kindly bear with my drawing skills. Now we are having data, and from that data we are plotting a graph by taking particle size on x-axis and frequency, nothing but the number of particles having that particular size on y-axis. Now we'll be getting some data. So for example, if we get a graph like this graph indicates the distribution of particles or the distribution of globules according to their sizes. Now this plot is known as size distribution curve because we are considering the particle size and its distribution, number of particles distributed having a specified size. Hence, it is known as size distribution curve. Now, from this curve, we'll be able to see how many particles are being distributed and how many particles are sharing the same particle size. Now, from this graph, the peak point of this graph represents the average particle size of the globule. Now, what is the importance of plotting this graph? Now, for in case, consider an emulsion, a newly formulated emulsion. Now, take a sample and check for the particle sizes and the frequency and do a graph size distribution curve for that point time. For example, see, soon after we formulate an emulsion, on the day 1, we'll be doing the size distribution curve analysis. Now, keep this emulsion aside for a span of 30 days, and at the end of 30th day, do the same analysis, size distribution curve analysis, and we'll be able to see a curve. Now, if there are some changes in the shape of the curve on the 30th day, then we can say that there is some unstable reaction that has occurred in our emulsion. Why? Because during its shelf life, if proper proportions of internal phase and external phase is not maintained, if proper emulsifying agent is not being added, all the globules will tend to come closer and they fuse to form a larger globule, right? So because of the change in the sizes, right? Because of the change in the sizes, there will be some change in the graph also. The change, for example, if they are unstable, the larger particle size will be considered. So the particle sizes will be increased and the curve of the graph will be changed. So that is how the stability of an emulsion is determined by size distribution curve analysis. We should make sure that the shape of the curve should not change. If we observe any changes, that represents the change in the number of globules, the change in the size of the globule. Hence, we can easily say the emulsion has become unstable. So, that is how we can consider or we can estimate the stability by means of size distribution curve analysis by the help of microscopic method. There are other methods by which we can count the number of globules, which include Coulter counting, turbidimetric analysis, and temperature tests. The name itself indicates Coulter counting includes the counting of the globules when they are or when an emulsion is placed in the Coulter counting machine or an instrument. Now, let's see the other methods by which we can assess the stability. Apart from the microscopic method, we do have another method by which particle size can be determined is by Coulter centrifugal photosedimentometer. So, let's see the principle involved in this method. The name itself indicates Coulter centrifugal photosedimentometer. This meter or this instrument helps us not just to measure the particle or the globule size, it helps us even to count the number of globules per millimeter of an emulsion. So it is a very sensitive instrument which gives the information of both the particle or the globule size and the number of globules present in an ml of emulsion. There are other methods that are commonly used to determine the stability of an emulsion, which include freezing method, freezing on thawing method, and centrifugation method. Out of all these three methods, it is the centrifugation method that is commonly used. It is an analytical method that is used to determine the stability of emulsion. Now let's see the centrifuge method, which is most commonly used technique in the laboratory. In this method, we will be using ultracentrifuge instrument to determine the stability of an emulsion. How does this centrifuge act? Now, this is the centrifuge that is used to study the stability of an emulsion. This is a basic one. And this will be placing centrifugal tubes that are filled with our emulsion. This instrument is run at a specified speed, and after specified time interval, this machine is stopped and the centrifugal tube having the emulsion is taken out to check for the sedimentation. Now, if in case our emulsion is stable enough, there will be no separation of phases. Now, if the emulsion is not stable, because of the centrifugal force during centrifugation, the oil particles and the water particles will tend to get separated. So we'll be able to say a separation of the phases. And on further rotations, a complete separation of oily phase and the water phase is seen. So this separation occurs if and only if our emulsion is not stable one. If our emulsion is stable, then we'll be not able to see any separation of the phases, oily phase and the aqueous phase. This is how we'll be making use of centrifuge method to determine the stability of an emulsion. Now let us see how can we encounter all these problems. Till now we have seen the different problems that we see during the formation of emulsion and the reasons behind those instability problems. Now, by considering all these parameters, we being a pharmacist, we need to encounter all these problems to get a stable formulation. Now let us see one by one. The first instability problem would be creaming. Creaming is a phenomenon of the migration of the oily phase and the aqueous phase based on their density differences. So to avoid these density differences, we need to improve the viscosity of the dispersion medium. If the dispersion medium or the external phase is more viscous, then there will be less chance for the migration of oily phase or the aqueous phase. So in order to improve the stability, we need to add viscosity enhancers. Viscosity has to be improved or increased to avoid the migration of different phases. And in such category falls methyl cellulose, tragacanth, sodium alginate, gelatin. These are majorly used to improve the viscous nature of the formulation. And again, we need to decrease the globule size. The other one is by decreasing globule size. So if the globule size is decreased, reduced, or uniformly made, the chance for the fusion of the globules will be reduced. The coalescence chance will be reduced. We should make sure that the globule size are uniformly distributed with a minimum size. And again, by decreasing the density differences, which is the major cause for the creaming. So these are the three different ways by which we can avoid creaming and thus we can improve the stability. And the next one is coalescence and breaking. Coalescence and breaking goes hand in hand. A fusion of all the globules together to form a bigger one, and then complete separation of the oily phase and aqueous phase is seen in this kind of instability. To avoid this, we should make sure that the particle or the globule should be uniform. We should make sure that the uniformity of the particle and globule is maintained. And again, by improving the viscosity of an emulsion, thus preventing the flocculation and coalescence. And the third one is, the most important one is maintaining phase volume ratio. Maintaining phase volume ratio is very important in maintaining the stability of an emulsion. We should make sure that the internal phase and external phase should always be in equal proportions, more or less 50:50 proportions. We'll get more stable one. If in case, if the internal phase or the external phase, if they have different proportions than the prescribed proportion, then there might be a chance for coalescence or a fusion of globules. We should make always sure that the dispersed volume or the external phase, the dispersed volume should always be lesser than or equal to 74%. Should not be more than that. But mostly, for the most stable emulsion, the phase volume ratio to be considered is 50:50 or the 50:50. If in case, if our formulation needs a more internal phase, if our formulation tends to be a solid emulsion, solid kind of emulsion, then we being a pharmacist, we need to improve or we need to increase the quantity of internal phase, right? So if in such case, if you want to increase the volume of internal phase, you should make sure that it should not exceed 74%. That is the most important one, the phase volume ratio. And the next one is physical and chemical changes. The name itself indicates we'll be able to see some changes if emulsion undergoes some unstable uh, reactions. This type of change is majorly seen if proper emulsifying agents are not used in the formulation. For example, most of the natural emulsifying agents, they are more susceptible for bacterial growth. Hence, it might result in emulsion deterioration or degradation. Hence, to avoid such kind of changes, chemical changes because of bacterial growth, it is always preferred to use synthetic emulsifiers. And the next one is phase inversion. Phase inversion is a phenomenon where the internal phase, the supposed to be internal phase, turns out to be external phase, and the supposed to be external phase turns out to be the internal phase. This actually occurs because of improper choice of emulsifying agents, and also improper usage of emulsifying agents uh, in improper concentrations. And also for phase inversion, the major problem or the major reason will be the phase volume ratio. If a proper phase volume ratio is not maintained, then it results in phase inversions. You should always make sure that the internal phase and external phase should be in equal proportions, 50:50. But if we wanted to improve if the particular formulation demands more internal phase, we should make sure that internal phase should not be more than 74. If that is happening, then your internal phase is no more an internal phase. It turns out to be external phase. So these are the reasons and the proper ways to encounter the instability problems that occur during the emulsion formulations. Now let's see what are the rheological considerations of an emulsion. This is the important concept. Now, we being a pharmacist, what is actually making us to correlate our formulation with that of a rheology? Is it really important to know or to consider the viscosity parameters or the flow properties of a formulation like emulsion? Yes, it is really important. So, we being a pharmacist, it is not just to formulate an emulsion or to formulate or to manufacture a formulation. It is our duty to even store the formulation properly. So, most of the emulsions, they can be formulated as creams, lotions, uh, dilute formulations, cosmeceuticals, creams, semi-solid creams, jellies. So all these will are actually uh, have the characteristics of an emulsion. For example, uh, let's consider lotions and creams. They show a non-Newtonian behavior. Let's recollect what is non-Newtonian behavior. Give it a thought. Just recollect the Newtonian behavior versus non-Newtonian behavior. Okay, let me continue with this. Non-Newtonian behavior, which is non-Newtonian systems, are the systems which show a change in the viscosity when a stress is applied. Newtonian systems are the systems where viscosity is not changed even if you apply stress. For example, water, when you forcefully pressurize a water, the viscosity of the water will not change. When you pressurize a system like a syrup, the viscosity will not change. The viscous nature of the syrup will remain syrupy, will remain viscous. But whereas few formulations like lotions and creams, they exhibit non-Newtonian behavior. For example, when you take out a lotion out of a container or a cream out of a container, when you apply the cream over the skin with some pressure, the viscous nature of the cream decreases and gets easily applied over the skin surface. When you look at the molecular level, the viscous nature of the cream in the container will be more than the viscous nature when it is being applied over the skin, right? Means what? When you are applying some stress or force while applying, the viscous nature gets reduced or gets changed. So this change in the rheological behavior, this change in the viscosity behavior, viscous nature, is seen in the non-Newtonian system. So the lotions creams that come under the emulsion, they exhibit or show non-Newtonian behavior. Similarly, most of the cosmeceutical creams or semi-solid preparations, they exhibit non-Newtonian behavior, especially the plastic behavior. Only when you apply with a specific force, then will be able to easily spread the particular cream or cosmetic, say some foundation or any cream can be easily applied over the surface, skin surface. Similarly, few other semi-solids, creams, jellies, they both exhibit uh, both the characteristics of viscosity and elasticity. So they can be called put together as a viscoelastic property. Now, is it really important to consider all these viscosity or the rheological behaviors of various formulations? Yes, of course. So if we get to know the behavior of all these formulations, we'll be able to decide the type of the container, right? Now, that is why most of the ointments, they are given or they are stored in tubes having different shapes of nozzles. When you pressurize it, the ointment present in the tube will extrude through the narrow opening of the ointment, and because of that force, the ointment gets a little liquefied and it comes out easily. Now, let us consider these emulsions from the consumer point of view. Now, how can we improve the rheological behavior of an emulsion? We, being a pharmacist, we need to have a thorough knowledge on the type of emulsifying agent to be used in the particular type of emulsion, and the amount of emulsifying agent to be used also to be considered. So, from a consumer point of view, do always remember it is preferred to formulate a shear thinning emulsions. The name itself indicates when you pressurize the system or when you apply some force or the shearing stress, the viscous nature of the formulation will be less viscous. Shear thinning emulsions are to be preferred. Why? Because shear thinning systems are to be preferred because consider a lotion bottle. When you keep lotion uh, to stand for some time, it gets thickened, and when we are supposed to use the lotion, we'll be shaking this container and then we'll be using it. When we are shaking the container, we are actually stressing up the system, and the viscous nature of the lotion inside the container decreases so that it becomes easily pourable, right? So we should always make sure that the emulsions, when they are formulated as lotions, we should always make sure that it has shear thinning properties. And again, thixotropic property and shear thinning property are preferred to get a stable product. Let's recollect the thixotropic behavior. What is thixotropic or thixotropic behavior? Thixotropic behavior or the thixotropy study includes a time-dependent changes in the viscosity at varying shearing stresses. When you increase the shearing stress, there will be a change in the viscosity. When you still increase the intensity of the stress, there will be a change, a different range of viscosity change will be seen. For example, the same principle, the same example which we have uh, referred for shear thinning emulsions. When we are keeping the lotion away undisturbed for some time, what happens? All the particles or all the lotion will come together. They form like a gel consistency, a thick mass, right? And when we are shaking the container, all the molecules or all the particles will get loosened up and it becomes easily pourable. And such phenomena where gel to sol is seen. So here this is much preferred because there will be a transformation from a gel to sol and sol to gel. So it becomes a tight mass when you keep it undisturbed, and when you shake it, when you are applying some shearing stress by shaking, the molecules or the particles get loosened up and it becomes pourable. Loosen up means it turns out to be a sol, and then when you keep it aside, it becomes again a gel consistency. This is how the thixotropic behavior of an emulsion is explained. So for an emulsion, both it should exhibit the shear thinning properties and also thixotropic properties. The next one is preservation of an emulsion. Is it really important to preserve our emulsion? Yes, it is really important. Why? Let's see in detail. As emulsion has both oil phase and aqueous phase, it is really important to add a preservative. Why? Because the aqueous phase, the water, is more susceptible for microbial growth. So it is always necessary to add a preservative. Emulsifying agent can also in few concentrations can act as preservative. But then there are few categories of emulsifying agents which are prone for bacterial growth, like non-ionic, anionic emulsifying agents are prone for bacterial growth. So if our emulsion consists of this type of emulsifying agents, then we should make sure that we need to add preservative, or else the bacterial can easily degrade non-ionic and anionic type of emulsifying agents, like uh, most of the natural gums, glycerins, natural gums that include tragacanth. They are easily degradable by the bacteria. So it is always necessary to include a preservative in an emulsion in an adequate concentration. Now what happens? Is it really easy to add a preservative in an emulsion? No, it is not an easy task. to add a preservative in an emulsion. Why? Because we should make sure that the preservative which we add will get equally partitioned between the oily phase and the aqueous phase. As the emulsions are heterogeneous systems, means they have both aqueous phase and the oily phase, the preservative that we add should actually partition between the two phases. Now, in this concept of adding preservative to an emulsion, we should recollect our ionization and unionization part. Now, let me ask you some question. Uh, is it unionized molecule will be absorbed much faster, or ionic I, ionized molecule will be absorbed faster? Let me ask you. Absorption of molecule, which is faster, through membrane, ionized or unionized? Just give it a thought. It is an ionized molecule or the particle or the chemical group will be absorbed, right? So we should make sure that the preservative that we add in our emulsion should attack or should be absorbed by the bacterial membrane. So we should make sure that the preservative must be present in unionized state. Now let's recollect the relationship between ionization and pH. Are these two related with each other? If so, how they are related? For example, if a drug is uh, ionized, say let this drug be a weakly acidic drug. If this drug remains ionized in, okay, let me ask you, a weakly acidic drug will remain ionized or unionized in acidic pH? How will the weakly acidic drug exist in acidic pH or acidic medium, ionized or unionized? Unionized. So similarly, the same with the weakly basic drug remains unionized in basic pH. So we should always make sure if we are adding weakly acidic preservative, we should make sure that the emulsion is having a weakly acidic pH. So always make sure that if we are adding a weakly acidic preservative, make sure the pH of aqueous phase in emulsion should be maintained low, just to make sure the preservative remains as unionized and hence it penetrates through the bacterial membrane. And if the preservative is weakly basic, then we should make sure that the pH of the aqueous phase in the emulsion should be maintained and at the weakly basic level. In short, it is only the unionized, unbound, and free species or free molecules of preservative is effective. So while adding or while uh, choosing the type of preservative, we should make sure that the preservative remains unionized. We should check for the pH of the preservative so that we need to maintain the same kind of pH in emulsion. We should make sure the preservative gets partitioned equally between the aqueous phase and the oily phase. And that is how we can improve the stability of an emulsion. In this lecture, we discussed about the type of instability problems that we see and how can we encounter or how can we overcome these type of unstable problems and the various rheological behaviors of different type of formulations that are considered as emulsions. And we have discussed about the importance of addition of preservative into the emulsion. And the most important point of this lecture is the methods to assess the stability of an emulsion. So we discussed about the microscopic method, ultracentrifuge method. So by these two methods we can actually determine the stability of an emulsion, and if this emulsion is found to be unstable, we can improve this stability of an emulsion by considering various measures that we have discussed in this lecture. If you have any doubts regarding this lecture, you can contact me through mail. Hope you all got the points. Just go through this. If you find it difficult, you can ask me through mail. Thank you.